So, hello everyone. Today I'm happy to be here to introduce our work on generate effective test cases from SMT formulas. So I'm Chengyu Zhang from ETH Zurich. So let's get started from a very basic concept of the software testing. What is a test case? Test case is essentially consists of a test input and the corresponding test oracle. And we use test input as the input for the software and check the output of our software with test oracle so that we know whether the software behaves as we expected or not. So, but design such kind of test cases is very headache. Like people don't want to do that. So there is a huge community that people want to actually automatically to generate test cases for our software. And ideally, we can check our output of our software with our corresponding test oracle. But here, the problem is that if the test input is automatically generated, how can we get the corresponding test oracle? It's very difficult. So it's known to be the test oracle problem. How can we generate a test input as well as its corresponding test oracle? So this work is trying to tackle this very difficult problem. So in this work, we actually proposed a way to solve the problem by transform the SMT formulas into test input. And then we map the satisfiability to the test oracle, then to use the SMT solver to get the test oracle for free. So in case some of you may not know what SMT is, I give you a very brief introduction. So SMT problem is actually to ask whether given a first order formula, for example, this one, x less than 0 and x greater than 1, whether we can find an assignment for x that makes this formula become true. Like for this formula is unset because we cannot find an assignment for x that makes this formula become true, but if we change the 0 to 2, then this formula becomes set because we can find assignment like x equal to 1.5 to make this formula become true. Okay, so it's SMT problem. And the SMT solver is a tool to automatically solve the SMT problem. For example, given an unset formula, it will automatically give unset. And if we give it a set formula, then it will automatically give set. Okay, so it's a tool we can use. So within our framework, we actually here the SMT formula is essentially the first order logic formula, and the satisfiability is essentially the set and the unset answer. So why we use SMT formula to transform to the test input? Because it's very expressive and also it's diverse. And also we have many benchmarks, and also we have like SMT fuzzer to generate a bunch of test like SMT formula that can transform into test input. And also, we have very mature SMT solver that is mature, efficient, and accessible. For example, Z3 and C5 that are accessible to people. So we can use the off-the-shelf SMT solver to get our test oracle. So there's the two core problems in our framework. The first one is how can we transform the SMT formula into test input, and second one is how can we transfer our satisfiability into the test oracle. So we will demonstrate how we do that in the context of testing program verifier. So what is program verifier? Maybe it has been introduced before, but here is some very brief introduction. That given the program and the corresponding specifications, the program verifier is to automatically check whether the program is safe or unsafe regarding the specification or the properties. For example, given this piece of code written in Dafny, Dafny is a program verifier and also a program language that can automatically compile to the code, which has been introduced today in the keynote, which had been widely used in Amazon in their development process. Okay, and this piece of code is written in the Dafny language, which actually is very simple program, so we can actually go through it. So we just demonstrated using the reachability property. What is reachability property? Reachability property is to ask whether a certain point in the program can be reached or not. For example, I will ask whether this assertion is reachable or not. If it is reachable, then the program should be unsafe because the assertion can be triggered. And if the assertion is unreachable, then it's safe because this assertion can never be reached. So this program is actually safe, right? Because first we calculate the time into the x cube, and then the first condition is we want time equal to 0. Once the time is equal to 0, the x must be 0. And then when x is equal to 0, the x is less than 2.0, and the last branch cannot be reached. So this program is actually safe. Do you agree with it? Okay. So the program verifier is actually the tool to automatically give the safe and unsafe answer to this program regarding the specification. But once it gives the answer, we actually don't know whether it's indeed correct or not. We just assume that it's correct, but it may not be the case. So there are many previous work on doing this. One from my previous work and one also from Dafny, and they want to know whether the program verifier result is correct or not. And what we essentially did is actually use actual execution as a reference for the verification process. So if our actual execution reports safe, then program verifier should report safe, right? For example, for this piece of code has the issue that it cannot be executed. So what should we do to validate the verifier? We need to make the x to be a concrete value. For example, assign x to 0. Then when the x is 0, the x cube is 0. So that we reach the first branch, we can go into the first true branch. And for the second branch, we can also go into the true branch. And for the last one, we cannot reach. So this program is actually safe, right? So program verifier, for example, definitely if it correctly reports safe to this program, we know that, okay, this result is correct. So there's no bug in the program verifier. However, our previous work actually has a very important limitation, which is this program needs to be executable. So for example, here the x needs to be assigned a concrete value to make this program to be executable, then we can validate the program verifier. But actually, it can actually lower down the difficulty of this program from the large space of the input space to a very concrete input space, which may not be very challenging for the program verifier. For example, for this case, if we get rid of this assignment, make the x to be a free variable, then program verifier actually cannot verify this program and report unsafe. It will be very annoying, especially when you develop that piece of code, but you cannot be verified it. So what should we do? Here, if we don't have the actual execution to get to know the corresponding test oracle, what should we do? So we actually can use our framework, like SMT2Test framework. Now we can transform the SMT formulas into our program. And then we also transform the satisfiability into the safety properties of the corresponding program. Then we know whether the program verifier reports the correct answer or not. So let's give an example. First, how can we transform the SMT formulas into program? For example, given this piece of SMT formulas is essentially the very simple formulas, how can we transform this formula into our code? First, we identify how many free variables in the formulas. For example, there are only x. So we build out the body of our functions with the input value x. Only one input value corresponds to the free variable in the SMT formulas. And then, according to the conjunction of the SMT formula, we build the control flow of our body. And then we have 3 if statements, and then we identify the term in the SMT formulas, which is x cube. Then we use the time value to store the value of this x cube. And then we build the first condition according to the first literal in this formula, and we build the second condition according to the second literal, and the third one according to the third literal. Okay, now we have our program. Then the second question is that how can we transform the satisfiability into our safety? So this one is very simple. We just use reachability safety that to put an assertion inside the program. So when the formula is set, the program should be unsafe. Otherwise, if the SMT formula is unset, the program should be safe. So in this case, since this SMT formula is unset, so the program should definitely be safe. However, program verifier, if it report unsafe, it appears to an issue in our program verifier. Okay, so to make it possible, we actually make a lot of transformation rules to make it possible, and also we design some kind of intermediate language to make it possible to transform to not only to Dafny, but also can transform to, for example, C programming languages to validate different kinds of program verifier. For example, Dafny, and also CPAchecker is one of the program verifier model checker for the C program. So for the evaluation what did we do for the evaluation? First, we pick some like SMT formulas from the benchmarks. There is a large number of benchmarks from the SMT competition, and then we use our SMT fuzzers, which I collaborate with my colleague Dominic Winterler, and he's also sitting here, and he will present later. And we propose a lot of like fantastic fuzzing techniques, like for example, semantic fusion, OOPFuzz, and type fuzz to generate more and more high quality and diverse SMT formula as a seed to transfer to the program. Then we can use this formula to transfer to the program and to validate the implementation of CPAchecker and the Dafny. So as a result, we actually found 6 bugs in Dafny and 8 bugs in CPAchecker, and most of them are very critical soundness bugs, which I will show later. And most of them are, some of them are actually historical bugs in the historical vision and has been there for quite a long time. So let me give you some example about the bug we found. The first one, the first is a bug in Dafny. Here is a very simple program. Maybe it's not that simple because it's not human readable, but we know that it's unsafe by construct our test oracle. So, however, Dafny just report safe to this program, which will become very critical problem because the program is unsafe, but the Dafny just gives is an incorrect guarantee to this program. So it appears to be a bug in Dafny that when the developer fixed the bug, they found out it still cannot report the correct answer because there is another bug in the boogie. So they are trying to fix the bug in the boogie, and they found out, oh, it still does not work. Why? Because there is another bug in Z3 on the 9 solver. So yes, it's a very tricky bug here, but it's also very critical because it gives the unsound answer. So the bug I'm showing here is because it's showing that our technique actually can find very complex and very deep bug in our program verifier, and it is very effective. And another bug is showing this technique actually not only like can find bug in Dafny, but also can transform to C program to validate our CPAchecker. For example, given this program is essentially unsafe. I will explain why it's unsafe. And the CPAchecker just correctly give unsafe to this program. That's fine. But once we change this variable type 1 into the corresponding expression, essentially the semantic of the program does not change. But CPAchecker just gives the incorrect safe answer, which also an unsound issue in the CPAchecker. It's very critical. And this is because that the CPAchecker, there is an unsound rewrite in the CPAchecker that rewrites the not b less or equal to 0 times a transformed to the b greater than 0 times a. So it seems to be a sound transformation, right? But no. When a is equal to not a number, the first expression actually evaluated to true, and the second expression is evaluated to false, which bring out the unsoundness into the CPAchecker. And the developer also fixed this bug. Okay, so as a summary, okay, so test oracle problem is very difficult, but in this work, we actually propose a way to tackle this problem is by transforming the SMT formula into our test input and also transform our satisfiability into our test oracle. And we demonstrate our effectiveness of our approach in the context of program verification, and it's shown to can find a very deep and interesting bug in our program verifier. So for the future work, there are still some limitation of our work we want to push forward in the future. The first one is that we want to suppose more features, not only the control flow feature, but also maybe other features, for example, the type, maybe the class, maybe the more complex data structures, and so on. And also we want to support more series, not only the arithmetic series, maybe we can suppose a string series, we can suppose the array, or so on. And also in our work, it's very difficult for us to generate loops. We can generate some very trivial loops, but it's not very easy to generate complex and effective loops. It's also the one we want to explore. And also we want to explain the application of our techniques, not only for test the program verifier, although it's very important, but we want to explain it to, for example, can test the database system or our compilers or our static analysis and so on. And we have some students are working on this. So the takeaway of this work is actually to tackle the test oracle problem, actually you may find a way actually to use the SMT formulas to generate effective test inputs and use the SMT solver to get the test oracle for free. So it's the end of my talk, and there is one more thing that I will be on the job market. So if you are interested in my profile or interested in my work, please feel free to talk to me. Okay, thanks for listening. I'm happy to take your questions.
Questions? Run right here.
Oh.
Okay, thank you for your nice talk. So I've got one single question about the rate of false positives. So I think your method is generating, long story short, it is just translating the SMT formulas into the programs that you will then feed to the program verifiers, right?
Right.
So there are many cases in when you are dealing with the program verifier that programs can be not passing the verifier, but by adding one or two assertions, it will pass the program verifier. So is such a case considered a bug in the verifier or not?
Okay, it's a very interesting question that you essentially you just mentioned about the incompleteness of the verifier. That it has, like for example, the first bug I presented, yes, in some sense it's debatable, but it should not happen in a very small case. Like for the large program, it can help. It can happen because actually it's very complex. The SMT solver may return unknown. But for the very short case, it actually should not happen because it's very trivial for the SMT solver to solve. How can the program verifier cannot solve the problem? And the second kind of the bugs we found here is actually the sunless bug. The sunless bug is not in this group. The sunless bug should report unsafe for any unsafe case for the program verifier. It's also showing to be the case. Yeah, so.
Okay.
Yeah.
Thank you for your answer.
Thank you.
Time for one more question, if there is. Yes.
So I want to ask, what's the relation between your work and maybe something like the property-based testing?
Property-based testing.
Property-based testing, you are just also taking a property and try to test cases.
Okay, it's a very nice question. It's a very nice question. I think according to, as far as I know about the property testing, it's actually a white box testing. We add the property inside the code, and we execute the program and to see whether the execution meets the properties we want, right? It's kind of like the property-based testing. But for our work, we actually is a black box testing. We do black box fuzzing. So the problem is that we actually, there's no property in our testing like process. We just have the test oracle. We want to validate the output of the program verifier. Although it's related to property, but the output of program verifier is just, it should be set or unset. So it's not a property for the program verifier, like rather than the program we put into the program verifier. So I think it's quite different from the program like property-based testing. It's not really the same thing. Yeah.
Okay, that's time. Let's thank the speaker one more time.